So with the understanding that linear independence of a set of vectors means that none of my vectors can be expressed as a linear combination of the others. So each one of the vectors in a linearly independent set is spanning some direction that the other vectors in that set cannot span. Right? There's no redundancy. Each one is making a unique contribution to the span of those vectors. And if any of the vectors in our set is expressible as a linear combination of the others, then our set is a linearly dependent set. So, for example, if I have even a single relationship between a set of vectors, like if I have three vectors in n-dimensional space, and the third one of them is some linear combination of the first and the second, then what's going to be true about the vector equation where I have a 0 over here on the right-hand side? So I think it's this 0 that's the intentionality behind this activity. We want to somehow connect this version of a linear relationship, a linear dependence between v1, v2, and v3, with this other version where one side of my equation is the 0 vector. So what's the connection there, do you think? What needs to be true about this equation with a 0 on the right-hand side that means the same thing as having this linear relationship among these three vectors? Should this equation need to be consistent with one solution? Should it need to be consistent with infinitely many solutions? Or should it need to be inconsistent? So if I take the first of these equations, 3v1 minus 5v2 is equal to v3, and I want to make it look more like this orange one here. I want to get a 0 vector on one side of my equation. So what's a good way to get a 0 vector on this equation?
Subtract v3 from both sides.
Subtract v3 from both sides. So if I do that, I get 3 times v1 minus 5 times v2 minus 1 times v3 is equal to the 0 vector. So what this tells me right away is that there is at least one solution to this equation, right? There's at least one solution to this thing, and it's the solution x1 equals 3, x2 equals negative 5, x3 equals negative 1. The question is, will there also be other solutions besides this one?
Yes.
Yes. How do I know that there's going to be more solutions?
If everything equals 0.
That's is equal to 0, Victor.
Yes, that is another example of a solution. If all of my coefficients were 0, that would also give me a solution. Because my right-hand side vector is the 0 vector, if I take what's called the trivial linear combination, where all of my coefficients are zeros, that's also going to satisfy this equation. This is the trivial combination.
The solution.
And so I know now that if I have this solution, I'm also going to have this solution. And those two are different. So as soon as I have two different solutions to a linear system of equations, how many solutions am I guaranteed to have?
Infinitely many.
Infinitely many. Exactly. So when we have a linear dependence, right, when there is a linear combination of two vectors that give us the other one, then we will have infinitely many different linear combinations that give us that. And another way to say this, right, is that as soon as I have one linear combination of my vectors that's non-trivial, that gives me 0, then I know I have linear dependence. Right? Because no matter what vectors we put into a trivial linear combination, we're always going to get that trivial combination to equal 0. Right? And so that's not a very interesting case, because every set of 3 vectors satisfies this. But if I have a set of 3 vectors that have a non-trivial linear combination, well, that's when things are interesting. So a non-trivial linear combination equals 0. That's when we know that my vectors are linearly dependent. So dependent means that there is a non-trivial linear combination of those vectors that gives us the 0 vector as the right-hand side. So with that in hand, so a set of vectors is linearly dependent if and only if this vector equation is consistent and it also has infinitely many solutions. It's going to have infinitely many solutions because as soon as we have one that's non-trivial, we're going to have infinitely many that are non-trivial. Because that's the nature of the solutions of equations. And so if we take the converse of this, by the way, sorry, the contrapositive, this set of vectors is going to be linearly independent if and only if this vector equation is not consistent with infinitely many solutions, But it's always going to be consistent because the trivial solution always works. Right? The trivial linear combination always works. So this is never going to be an inconsistent vector equation. We can always pick x1 and xn and everything in between to be 0. Right? So we're never going to have an inconsistent system. So if it's not true that it's consistent with infinitely many solutions, then it must be consistent with a unique solution. Only the trivial solution would work, right? In the case of linear independence. So for a linearly independent set, the only way to make a linear combination of those vectors into the 0 vector is to choose all of our coefficients to equal 0. That's the only possibility for a linearly independent set. So activity number 3 is going to be how we wrap up this section. See if you can figure out which part of the reduced row echelon form of this matrix is going to tell us whether or not this set of 5 vectors is linearly dependent or linearly independent. The reason that this was a challenging task, as I watched your teams do it, is, I hate to say I told you so, but way back at the end of the first chapter, remember the process of going from the reduced row echelon form of an augmented matrix back into equation form to find an expression for the solution set. And I mentioned that that was a step that you're going to forget. And 2 out of the 3 teams basically forgot it. So I want to show you what the third team did. This is team 3, so congrats to team 3. If we take the reduced row echelon form of this matrix, this is what it looks like. And so everyone got this, so that's good. But then to convert this back into equations, we have to remember that there were implicit variables attached to each of these columns, right? x1 times this first column, plus x2 times the second column, plus x3 times the third column, plus x4 times the fourth column, plus x5 times the fifth column is equal to the 0 vector, right? That's really the vector equation that this matrix, this augmented matrix up here, is intended to investigate. And so after we do the reduced row echelon form, we should put those variables back into the mix. We should take each of those rows and rewrite it as a scalar variable equation. So the first row is 1x1 plus 0x2 plus 0x3 plus negative 1x4 plus 0x5 is equal to 0. And so team 3 has written that here in simplified form as x1 minus x4 is equal to 0. x2 minus x4 is equal to 0 according to the second row. x3 plus x4 is equal to 0 according to the third row. And then x5 is equal to 0 according to the fourth row. And so this collection of equations binds together the values of x1, x2, x3, x4, and x5. But there's only 4 equations. So where are we going to get a specification for our 5th variable?
It's free.
It's free. Exactly. There's the terminology that we want to bring back into the mix from that last section of our first chapter, which is probably the most important section of the whole course, right? We have a free variable. 4 out of our 5 variables have their values determined by that 5th one. And what this team has done here is solved each one of the equations for its respective variables. So they've solved for x1, for x2, for x3, and for x5. But for x4, they just write x4 is equal to x4, right? And so they're thinking of x4 here as being a free parameter. We can choose the value of x4 to be anything we want to, right? And once we choose a value for x4, then all the other variables, x1, x2, x3, x5, are going to follow suit. They're going to fall into line. Once we pick what x4 is, it's going to determine the values for the others. And most notably, because we get a free choice for what x4 is, we can choose it to be non-zero. And as soon as I choose x4 to be non-zero, that gives us a non-trivial vector solution to this equation, which this team has written down here. For example, if we choose x4 equal to 5, then that makes x1 equal to 5, it makes x2 equal to 5, it makes x3 equal to negative 5, and this gives us a non-trivial vector solution. So as soon as we have a non-trivial vector solution, we therefore have infinitely many non-trivial vector solutions, and that shows that this is a linearly dependent equation. But we still haven't quite answered the question as it was originally posed, and that question is, what feature of this reduced row echelon form is telling us that story? How are we tipped off to the existence of a free variable by the form of this reduced row echelon matrix?
It's the 4th column.
What's happening in the 4th column?
No pivot.
No pivot. There's no pivot in the 4th column. Right. So it's good practice, and this is why our textbook authors do it, to always go through and circle or box or whatever all of your pivots in your reduced row echelon matrix. This first one is a pivot. This next one in the next column is a pivot. In the third row, third column, this one is a pivot. This one down here is a pivot. But we can only have at most one pivot in every row and at most one pivot in every column. And so if every row has a pivot, which is true, there must be a column which is missing a pivot, and that's this fourth column. So that fourth column that's missing a pivot corresponds to variable number 4, x4, can be taken to be a free parameter. And because of that, we can choose its value to be non-zero, and as soon as we do that, that gives us a non-trivial solution to this vector equation that gives us 0, which is how we know that this is a linearly dependent set of vectors.